Alrighty, everyone. So today, this week, we're going to talk about the math and physics of one qubit. And I picked out some readings for y'all. So Sutter Chapter 7 is kind of the main feature. And then this article from Durr and Heusler is a really nice discussion of what we can learn about quantum physics from a single qubit, because you can't do much with one qubit, but it's still interesting. There's a Medium article about quantum states in the black sphere, and then a couple articles related to Felix Bloch's work that received the Nobel Prize in 1952 on thinking about nuclear, the kind of the predecessor to NMR, nuclear magnetic resonance. So those should be fun. This article, for reference, is like a paragraph long. So that's basically what he got the Nobel Prize for, which is interesting. And then a reminder that problem set 2 and my favorite qubit problem set question is due on the 27th. A couple people have asked about, does each person in the team need to write a different problem set question? No, it's a team. You only need to write one good question and submit it. All right, so just to kind of reiterate where we're at, a qubit is a superposition state represented by a linear combination of vectors, 0 and 1 in the complex plane. And we can write that superposition state as A0 plus B1, where A squared plus B squared, the absolute values, are equal to 1. And through measurement, a qubit is forced to collapse irreversibly through projection to either 0 or 1 with a probability A squared and B squared respectively. And we call A and B probability amplitudes. And when we use the word collapse, we're kind of thinking about the physical interpretation of a quantum system where measurement causes a superposition to move into one of two choices for our state. And we can, of course, always convert our 0 and 1 quantum qubit states to classical bit values if that's convenient for some reason. All right, so when we think about qubits, we often represent them as points on our Bloch sphere, a unit sphere. So state 0 is at the North Pole, and state 1 is at the South Pole. And points on the sphere, any point on the outside of the sphere is equal to a quantum state. And a few people have asked, well, why do we represent our qubit states on a sphere if we just care about the surface of the sphere? And as we'll see today, we actually care about the interior of the sphere as well when we're talking about not pure states, when we're talking about mixed states. Mathematically, the qubit can be in a superposition, so we can not just have our pure 0 and 1 states, we can have a superposition of the two because it can be somewhere, anywhere on the sphere that's not the North or the South Pole as well. And a quantum algorithm is going to use several qubits together to make a quantum register, and from the viewpoint of a single qubit, this kind of process of manipulating the qubits looks sort of like this. So you start off with your qubit in its ground state, we'll call it 0. And then you're going to move the qubit into some standard superposition. Often that is achieved by applying the Hadamard gate and moving it into the XY plane. And then you follow your steps that are defined by your algorithm, and you apply some number of reversible operations, quantum gates, to your qubit. And then you get measured, and you always become 0 or 1 at the end. And you can read those out to classical bits if you want. And it's what happens in steps 2 and 3 that make quantum computing really interesting. For the Bloch sphere, step 2 means I get moved into some designated point on the equator, typically. And step 3 translates to getting moved to other points in the sphere. How do we do this? Well, we can, work with the Bloch sphere. That's one convenient way to do this. But typically, we're just going to be using linear algebra. So the math part is thinking about linear algebra in a 2D complex vector space. And as a vector, the qubit state has a length of 1, at least if it's a pure state. Linear transformations have to preserve that length. And so the matrices that do these linear transformations are unitary, as we've learned. Because they're unitary, they're invertible. So moving a qubit from one state to another is always reversible, and it's identical to doing them in the reverse order. When we build quantum circuits from our qubits, the only operation that's not reversible is measurement. And we can think about quantum circuits from a mathematical standpoint as the application of these unitary matrices to our vector spaces that are our vectors that represent our qubit states. But measurement is a physical action, and it drops us from our superposition states to either 0 or 1. And math gives us the probability of achieving one of those two states. It doesn't tell us which one we'll get for sure, just the probability of getting one or the other. Okay, so one thing that we kind of alluded to is that when we start working with our qubits, we're going to be using Braket notation, and I kind of walked you through some standard Braket notation from like chapter 2 of Nielsen and Chuang last week. But just to kind of reiterate so we're all on the same page, because I know this notation is new for some folks, let's remind ourselves what this is. So if we have a vector v that we define by some series of values, we can denote bra v as the row vector of the complex conjugates. So we would have v1 conjugate, v2 conjugate, up to vn conjugate. And we could similarly think about a vector w. We could define ket w as the column vector of those entries, not the conjugates. So then the two operations that we think a lot about when we're doing these manipulations are the outer product and the inner product. So the outer product, v times w, is equal to the outer product, which is v1 times the conjugate w1, v1 times the conjugate w2, etc. Write the rest, vn, w1. And our inner product is equal to v1 w1 plus v2 w2 plus vn wn. So when we think about outer products, they produce a matrix, and you might often hear them referred to as projections. And our inner product produces a value. And you can think about them as sort of the overlap between quantum states. And we can also think about the length of our vectors. So the length of our vector v, for example, is just equal to the square root of the inner product of v with itself. Okay, so hopefully that is pretty clear. So let's look at just a quick example to get our brain juices flowing. So if I have these two vectors, v and w, where v is 3 minus I and w is 2 plus I, comma 4, what is the inner product and what is the outer product? So I'll give you just like a minute to think through the answers to these questions. And then we can look at them quickly. Anybody get the inner product real quick? Yeah, 6 plus 7i. So that's just equal to 3 times 2 plus I plus 4i. What about the outer product? So the outer product is WV. This is going to give us a 2 by 2 matrix. And that 2 by 2 matrix is going to look like 2 plus I times 3, 2 plus I times I, 4 times 3, 4i. 4 which you can expand out really quick. So sometimes when we're working with our quantum states, we use symbols inside of our bras and our kets instead of numbers, just to label them. So we use things like 0 and 1 to imply certain things. So when we have our state 0 has the coordinates 1, 0. We're talking about our vector. And our state 1 has the coordinates 0, 1. And here it's implied that we're using the standard basis, E1 and E2, that has those coordinates 1, 0 and 0, 1. If we decided to use a different basis, a different orthonormal basis for these two quantum states, then they would be the same vectors, but they would have different coordinates. So just to kind of remind ourselves how to think about that, what are the coordinates for 0 and 1 if I had the basis u1 equals square root of 3 over 2, comma 1 half, and u2 equals minus 1 half, square root of 3 over 2? How would I approach this problem? All right, so if I wanted to come up with some desired coordinates, maybe x and y, I need to find the coordinates that satisfy v equals x times u1 plus y times u2. So if I want to do that for 0, I just write out my equation x square root of 3 over 2 plus y times minus a half. And that needs to give me 0. And then I have x times a half plus y times square root of 3 over 2. And that needs to give me 1 for 0. And so I can just go ahead and solve my system of equations, and I get x equals a half and y equals square root of 3 over 2. So my new coordinates for 0 in this basis is going to be a half square root of 3 over 2. And you can do the same thing for 1 and show yourself that 1 is just going to be square root of 3 over 2, comma 1 half, minus 1 half. So let's think about representing our quantum state again. So if we have our quantum state, A0 plus B1, that's a quantum state, and we know that the square of that state is a squared, the absolute value of a squared plus b squared. That's got to equal to 1. And that's the same thing as saying that the inner product of the state with itself is equal to 1. And the values, a squared and b squared absolute value, are non-negative numbers in the real plane. And they are the probabilities that our quantum state will go to 0 or 1 respectively when I measure them. So if I let a be some real number 1 half and b be square root of 3 over 2, then a squared is a quarter and b squared is 3/4. And that means that the state of the qubit has a 25% chance of collapsing to 0 and a 75% chance of collapsing to 1 when I measure it. So let's think about another situation where I have some number c in the complex plane with an absolute value of 1. So if I multiply this number c by my quantum state, I can re-express that as this equation here, Ca times 0 plus, and I can kind of expand this out to rearrange it to say that Ca squared is the same thing as absolute value of c squared times a squared, and that's just going to be a squared because we said that the absolute value of c is 1. And same thing with cb squared. It's just equal to c squared times b squared, which is just equal to b squared because, again, the absolute value of c is 1. So what's great about this is that this tells us that the probability of getting 0 or 1 upon measurement isn't changed if I multiply my quantum state by some complex number that has an absolute value of 1. So there's no observable difference when I do this multiplication. And we can remember that there's a nice way to express complex numbers that have an absolute value of 1. And what do they look like? Say it again. Yeah. So they look like, we can express them in polar coordinates. They look like e to the theta I, or I theta. We can also write them as cosine, well, I wrote phi, cosine phi plus I sine phi. So now I can re-express A and B in polar form. So I have my quantum state is equal to R1 times e to the phi 1I times 0 plus R2 times e to the phi 2I times 1. And if either A or B is 0, then the other is 1, and we have the basis kets. But if we assume that A is not equal to 0, and so R1 is not equal to 0, then I can rewrite this as follows. So I can pull the e to the phi 1I out front, and then write my second term as a difference. And the net result of doing this is the equivalent statement of saying A0 plus B1 is equal to R1 e to the phi 1I times 0 plus R2 e to the phi 2I times 1. And the coefficient of A for 0 is real. Then this is the same as saying that R1 0 plus R2 times e to the phi 2 minus phi 1I is equal, times 1, sorry. So what's great about this is that this comes back to this idea of the global phase that I introduced last class. So this leaves us with sort of 2 degrees of freedom for the state of our qubit if we're kind of expressing it in this final form. So the first state, the first degree of freedom is one related to the magnitude. Since R1 and R2 are dependent. And the second is the relative phase. The relative phase is significant and important, as we'll see down the road when we think about things like quantum interference, which is a useful technique in quantum algorithms. And the state of our qubit can be represented, like we just said, as R1 times 0 plus R2 times e to the phi I times 1. And we can also find an angle, theta, where 0 is less than or equal to theta, is less than or equal to pi, where R1 is equal to cosine theta over 2, and R2 is equal to sine theta over 2. And then we can rewrite our quantum state in terms of both theta and phi. So now we have that our quantum state is equal to cosine theta over 2 times 0 plus sine theta over 2 times e to the phi I times 1. And when two quantum states, psi 1 and psi 2, differ only by a complex unit multiple, u, where psi 2 equals u psi 1, then we can't tell the difference between the two when we measure them. So u is not observable, and we call that the global phase. So two quantum states that differ by a global phase give you the same result. Okay, so we talked about unitary matrices quite a bit over the last couple weeks. Remind me, what's a unitary matrix? So our single qubit gates, when we're talking about manipulating qubits, are represented by 2x2 unitary matrices. And in our quantum gates, the input qubit numbers and output qubit numbers have to be equal, and the action performed by the quantum gate is defined by multiplication of the unitary matrix by the vector. And our quantum gates are unitary because they're implemented via the action of a Hamiltonian. and that gives unitary time evolution according to the Schrodinger equation, because our Hamiltonian is Hermitian. So the possible measured energies of my state, the eigenvalues, are real numbers. So if my quantum state is expressed in this polar form, cosine theta over 2 times 0 plus sine theta over 2 times e to the phi I times 1. Let's keep the first probability amplitude real. Then what does a 2 by 2 unitary matrix look like that maps 0 to my quantum state psi? So I can write down U0. This has to equal U times my 0 matrix. And I want this to equal my quantum state psi. My quantum state psi, I know, is cosine theta over 2 plus sine theta over 2 e to the phi I times 1. So I can write down my matrix as follows, with some complex numbers a and b that are as yet undefined. So I have cosine theta over 2, sine theta over 2 e to the phi I, a, b. Okay, so now what can I do? So I have this matrix. A and b are complex numbers. Since u is unitary, I know that u times its inverse is equal to u times its adjoint. So I can write down the adjoint of u, which is cosine theta over 2, sine theta over 2 e to the minus phi I, complex conjugate of A, complex conjugate of B. And I can write down my inverse. So the inverse for a 2 by 2 matrix, we can just write it out explicitly, is 1 over the determinant of U times B minus A minus sine theta over 2 e to the phi I cosine theta over 2. And since u is unitary, I know that the absolute value of the determinant of u is 1. So now what I'm going to do to finish this problem is I'm going to choose some real number delta so that the determinant of u is equal to e to the delta I. So this is going to make my inverse equal to my adjoint. And so that gives me e to the minus I delta times B minus A minus sine theta over 2 e to the phi I cosine theta over 2 has to be equal to cosine theta over 2 sine theta over 2 e to the minus phi I conjugate A conjugate B. And that lets me define A and B in terms of these values, theta, phi, and delta now. So I have e to the minus I delta times B is equal to cosine theta over 2, and e to the minus e to the minus I delta A is equal to sine theta over 2 times e to the minus phi I. And B is equal to cosine theta over 2 e to the delta I. A is equal to minus sine theta over 2 e to the minus phi I e to the delta I. So now I can write down my matrix. So U is equal to cosine theta over 2 minus sine theta over 2 times e to the I delta minus phi I sine theta over 2 e to the phi I cosine theta over 2 e to the delta I. And I can do things to simplify this further if I want to like define some value that's equal to delta minus phi. For example, I can call it lambda and simplify this a little bit if I want. Yeah, so this is kind of a fun problem that walks you through the utility of knowing that my matrices are unitary. I have all these great properties that allow me to think about these kinds of transformations. So if I want to take a quantum state that has some probability amplitudes that I defined, then I can ask what does a 2 by 2 unitary matrix look like that maps one state to another state. So we have one more really cool tool when we're talking about quantum systems, qubit systems in particular, and it's called the density matrix. So when we have been representing the state of our qubits so far, we've been thinking about them as vectors. And working with this vector representation is convenient when we're dealing with states that can always be expressed as a linear combination of basis states, each with some associated probability amplitude. But in quantum computation and quantum communication, there's practical scenarios where that might not be possible, where we can't write down the state of our qubits as linear combinations of basis states. But instead, they have to be expressed as ensembles or statistical mixtures of multiple states, each with some associated probability of occurrence. So to do this, we think about something called a density matrix. And a density matrix describes the quantum state of a physical system, and it allows for the calculation of probabilities of the outcomes of any measurement performed upon a system, and they can be used to represent mixed states. So mixed states arise in quantum mechanics in two different situations. The first is when the preparation of the system is not fully known, and then that means that you have to deal with statistical ensembles of possible preparations. And the second is when you want to describe a physical system that's entangled with another, and its state can't be described as a pure state. So let's think about an example before we actually look at what the density matrix looks like. So imagine I have Alice and Bob again. Alice wants to send Bob a quantum state labeled plus. We'll learn about what that is in a second. And imagine that due to noise in the communication channel, there's a chance that there's a relative phase of the state that Alice is trying to send to Bob, that there's some probability of it flipping. So the probability that it flips to state minus is P. And so that means Bob could end up with the flip state minus with probability P, or with the desired state plus with probability 1 minus P. So Bob's state is either plus or minus. It's not a superposition of the two. And so if we want to know what will happen to Bob's qubit after he, for example, applies some gates and performs a measurement, we'll have to consider both of these cases separately. And this isn't too challenging if we're just dealing with two states, but in situations where the number of possible states is larger, keeping track of how each of these states evolves individually can become really impractical. And that's where this idea of the density matrix representation comes in handy. So the density matrix is an alternate way of expressing quantum states. And unlike the state vector representation, it allows us to use the same mathematical language to describe both these more simple, pure quantum states that we've been talking about so far, as well as these mixed quantum states that I just described in my Alice and Bob example. So this is allowing for imperfections in our systems. All right, so what is the density matrix? So if I have my quantum state, A0 plus B1, we can define the density matrix of our quantum state to be something we typically write as rho. And rho is the outer product of the quantum state with itself. So if I just write down what that is, that's my column vector AB times my row vector conjugate, A conjugate, B conjugate. So if I just multiply those out, I get A squared times AB conjugate times BA conjugate times B squared. Okay? So it's pretty simple. And we typically use rho to represent our density matrix. And what's nice about rho has lots of great properties, but you'll notice that the trace of rho, for example, is equal to 1. And rho is, in our case, always going to be Hermitian. So if I was expressing my quantum state in the polar form that we talked about earlier, R1 times 0 plus R2 times e to the I phi times 1, where R1 and R2 are real numbers, they're non-negative, then how would I express the density matrix? All right, so what are the two matrices that I need to multiply? What outer product do I need to take? It's going to look like R1 times R2 e to the I phi times the conjugate row vector, R1, R2 e to the minus phi I. So when I go ahead and multiply those out, I get R1 squared, R1, R2 e to the minus phi I, R1, R2 e to the phi I, R2 squared. And the density matrix is always going to be independent of any global phase, just like our normal, the case was with our normal vector notation. So we could have introduced density matrices in the context of general quantum systems. There's a whole framework of quantum mechanics. You can kind of re-express all the postulates of quantum mechanics from the lens of a density matrix. And Nielsen and Chuang has a nice section in chapter 2 that does that if you're curious. But for us, we're just going to be thinking about them in terms of our qubits. So it's nice to look at it this way because they're a lot simpler. Okay, so let's talk about observables and expectations. So we talked about these in general last week, but let's talk about them when we're thinking specifically about our qubit systems. So the matrices, M0, the outer product of 0 with itself, and M1, the outer product of 1 with itself, we call these projectors, and so they're Hermitian. And if we define our quantum state as being A0 plus B1, then we can define this inner product, psi with M0 psi, and we can re-express that as psi times 0 times the two inner products, which we can simplify to two simpler inner products. And we can go ahead and write down what this looks like in the context of our quantum state. So what does it look like? So we have the conjugate of A times the conjugate of B times our column vector 1, 0 times our row vector 1, 0 times A times B. So that's just equal to A, B times A, 0, which is just A squared. Similarly, we can write down the inner product psi m1 psi, and that's just going to give us B squared. So these expressions, these inner product expressions, tell us that A squared is the probability for measuring 0, and B squared is the probability for measuring 1. And we know that the eigenvalues of m0 are 0 and 1, corresponding to the eigenvectors 1 and 0. And m1 has the same eigenvalues with the eigenvectors reversed. And m0 and m1 we call observables. They're Hermitian matrices whose eigenvectors form a basis for the quantum state space. So it's kind of nice to, now that we sort of have our qubit systems, to go ahead and write out what these expressions look like so you sort of know where these come from in the math. Okay, so let's turn it around. Suppose I have an observable A, and A is a Hermitian matrix with eigenvectors E1 and E2 that correspond to eigenvalues E1 and E2. By definition, I can write down that A E1 equals E1, the eigenvalue, times the eigenvector, and A E2 is equal to the eigenvalue E2 times the eigenvector. And we can assume that the eigenvectors E1 and E2 form some orthonormal basis in our complex plane. And if our quantum state is equal to A times E1 plus B times E1 with the inner product of psi with itself equal to 1, then by the properties of the inner product, we can rewrite A as the inner product of E1 with psi, and B as the inner product of E2 with psi. And so that lets us write down that our quantum state is equal to the inner product of E1 times psi times E1 plus E2 times psi times E1. And this basis is related to A. So when we measure the observable A, the probability of getting E1 is E1 times psi, sorry for my bad symbols, squared. And the probability of getting E2 is just E2 times psi squared. Okay, so let's think about, now that we have a set of values and corresponding probabilities for when we might get them, it's reasonable to talk about expectation. So the expected value, we write it as A in brackets, of A, given that our state psi is equal to this expression here. We can simplify this. We can write down the same thing, and we can rewrite it in this form because we know that the inner product of E1 with the quantum state squared is just equal to this product of inner products. Same kind of logic here. And what's awesome when we kind of just march through all of this math is we get back to this form of the expectation expression. So the expected value of A is equal to the inner product of the quantum state times A times the quantum state. And what's fun about kind of working through this using the bracket notation is it really does show the elegance of it. So we get back to sort of what we started with. It all sort of squares and makes good sense. And we don't have to write out too many funky matrices. Let's stop there for today. And then next class what we're going to do is bring it back to the sphere. We'll talk about the density operator kind of interpretation on our quantum sphere. And we'll talk about specific quantum gates and how they move us around in the quantum sphere and what they do mathematically to our qubits.